Okay, today we're going to be looking at the representation of continuous data using histograms. So let us first consider what continuous data looks like and some of the problems that continuous data has. So when we have continuous data, the data can take any value. Therefore, we have rounding, e.g. to 3 significant figures or 2 decimal places or the nearest 10, depending on what the data is. So we need to be aware of this. So when we're rounding, there's going to be gaps between class values, and this can lead to a misunderstanding of the data that's there, that there's gaps which don't actually exist in the real data. So let's consider heights of a group of children, say, and these are given between 146 centimeters to 150, 151 to 155, and 156 to 160. So let's look here. What if we have someone who is 150.5? Well, it looks like that person will not fit in this class or that class. So you can see that there has the appearance of a gap in the data here and here. And these gaps would be 1 centimeter in height. Because we've rounded these values up, we need to make that clear when we're dealing with the data. So let's use H for height, and so we're going to rewrite the classes. So the actual classes are going to be, now if you think about what's the smallest number that could be rounded to 146? Well, 145.5 could be rounded up to 146. So we could have somebody of this height in their data. So H here could be 145.5 is going to be less than or equal to the height. Or H can be less than 150.5. Now on the upper limit here, we don't have it being equal to 150.5, but just but less than, because in the next class we'll start with 150.5, and that's going to be less than or equal to the height, and therefore and that height can then be less than 155.5. And then in our final class, we've got 155.5 less than or equal to H less than 160.5 centimetres, and these are all in centimetres. The classes, so we've got the lower and upper boundary values, and we're going to show this in on a number line. So here's our number line, which is kind of straight. So here we're going to have, let's make it a bit bigger, 145.5. We've got 150.5, 155.5, and 160.5. And let's change the colour here a wee bit. Let's do dark blue. So on our lower boundary, we can be equal to, so when we do equal to, it's a circle which is coloured in. And let's make this I'll just leave it like that. I'm going to make it thicker, but it's going to be too fiddly. And then this one is just less than, so it's not equal to 50.5, so this is going to be an open circle. But on the next class, we've got our closed circle again, and then our open circle, then our closed circle, and our open circle. Now we're going to have our class mid values, so the middle number that this can take. So this will, for this one, it will be 148. So the class mid values are going to be, so we take our 145.5, add it to 150.5 and divide by 2, and we get this. For here, the mid value is going to be 153. So again, we take 150.5, add 155.5, divide it by 2, and we get 153. And the final mid-class value is 158, because 155.5 plus 160.5 divided by 2 give us this. And we have the class widths, I'll write these up here. Just underline that so we can see it. I might write this in another colour just so it stands out a bit more. So for the class widths, we're going to have 150.5 minus 145.5, and that gives us 5. And we have 155.5 minus 150.5, again that's going to be 5, and similarly this class width is also 5. Now let us, when we've got this kind of data, the best way to deal with it and to look at the data, this kind of continuous data, is in a histogram. So let us look at histograms in more detail. A histogram is the best way to display discrete data. Sometimes the data will be grouped as a frequency table. So if you had, for example, the ages of some students, we could call it A years, and we have the number of students and they're taking a test. So NO is an abbreviation for number, and we'll call that F because that's the frequency of a particular score. And so this is going to be test scores out of 100. Oh dear, it's a very bad line. So we've got the age between 16 is less than or equal to A is less than 18, so between 16 and 18. Between 18 and 20, and between 20 and 22. And the number of students is going to be 34, 46 and 20. And the score percentage is the, again, number of students so between 10 and 29 gets 6. Between 30, 6 students score between 10% and 29%. Between 30% and 59%, there is 21 students, and between 60% and 79%, there are 60 students, and 8% to 99%, 13 students get this high grade. So the first table up here shows 3 classes, so these are the 3 classes of continuous data, and there are no gaps between the classes because we've got 16 is less than or equal to the age, and it goes up to 18, but 18 is included in this in the second class. So you see there's no gaps in the classes. The classes have an equal width of 2 years, so 18 take away 16 is 2. So the class width here is 2 years, which means we can represent the data in a frequency diagram by drawing 3 equal columns, with each column has heights equal to the class frequencies. So I'm going to have to get a fresh page up to show you to show you how to draw the histogram. So I'll lose this table, I'm afraid. But let's get one up. So here is our graph paper. Now, so what we would have on the, I might change the colour just so it makes it stand out more. So on the x-axis, we're going to put 0 here. Let's see, why is this not working? No, it's not going to work. Okay, we'll just do it here. So here is our origin, and what we're going to do is we're going to have like a zigzag line here showing that part of the axis shows a part of the range that's omitted. Because we start at age 16, we're not going to put in the years 0 to 16 because we don't have the data for those. Well, they're not obviously part of this group of students because they're too young. So that just shows that those ages are omitted. So we'll start here. Let's just draw our x-axis. So this would be 16, and we're going to have 17, 18, 19. So we'll do 17 here, 18, 19, 20, 21, 22. So we've got equal gaps, and then on the y-axis we have our frequency. So we've got 10, 20, 30, 40 and 50, and so we'll have our y-axis up here. Oh, it's terrible. And then we had, for the first class, so the first class 16 to 18, the number of students there was 34, and then I'll just write them down so we can. Second class we had 46, and the third class we had 22. 20, sorry. So for 16 to 18 we had 34, so it's going to be up here, and then 1, 2, 3, 4 is hard to see, so it's up to 18. When you do this yourself, you'll need to have rulers and just make sure it's really quite clear what you're doing. Then for the next class, 18 to 20, we have 46. 1, 2, 3, 4, 5, 6. It's about there. It's not very neat, I'm afraid. And the final class, 20 to 22, we had 20. Now, when you draw your histogram, make sure you label your axes. So this is age in years, and this is frequency. Now, the columns here and the frequency of each of the three classes, we can look at, if we look at the area, so I'm trying to think where to put this. Right, we'll just write it. I'll try and fit it in here. I'll write it up here, but it's good. Yeah, just so I can have it beside the histogram so you can see it. So let's think about the area of each column. So we'll think about the area and the frequency. So it's very not neat. So in the first class, the second, and the third. So this is the first, the second, I'll write a 1 in it. First class, the second class, and the third. So the area is 2 times 34, which is 68. It's not very clear, I'm afraid. And this one is going to be 2 times 46, which is equal to 92. And on the third, we've got 2 times 20, which is equal to 40. And the frequency, we've got 34, 46, and 20. So if we look at these numbers as, so the area ratio, we have 68 to 92 to 40, and then the frequency, we have 34, 46, and we have 20. So the ratios are the same. The area of the column to the ratio of the frequency are the ratios are the same. That shows us that the area is proportional to frequency. And this holds for every histogram. Sometimes you're going to have the class widths are not going to be equal. So we've got 2 years here, but you can have histograms where the class widths are not equal. However, even if the class widths are not equal, the area of each column will still be proportional to the frequency, and that's just a property that histograms have. If the class is not equal, if the class is not equal, on the y-axis you would have frequency density. So the frequency density means it measures the frequency per standard interval. The simplest and most commonly used standard interval is 1 unit of measurement. Let's look at this in a bit more detail. So we have, I'll change the colour back to black. If we require a column to represent 85 objects, and the mass is going to be 50 less than or equal to whatever the mass is, less than 60 kilograms. Then the appropriate standard interval is 1 kilogram. So height is going to be area divided by width. Therefore, frequency density is going to be, so you need each columns to represent 35 objects, so 85 objects. 85 divided by, well, the class width is going to be 60 minus 50, so that is 8.5 objects per kilogram. You could do this in grams as well, where you would have, if you changed kilograms into grams, you'd have a frequency density of 0.0085 objects per gram, and you would choose units depending on what is going to be the most practical for you. So for a standard interval of 1 unit of measurement, so 1 there, frequency density is equal to class frequency over class width. And you can rearrange that to be class frequency is equal to class width times frequency density, obviously. That's stating the obvious, just rearranging the formula. In a histogram, we can see the relative frequencies of classes by comparing column areas. And we can make estimates by assuming that the values in each class are spread evenly over the whole class interval. And so we're going to see an example of that next. Okay, so we're going to look at a problem where we're going to have unequal widths for our classes. So the masses why is this not working? The colours changed, that's why. There we go. The masses in kilograms of 100 children are grouped together into two classes. And we've got this table, so we've got our mass, and our first class is going to be 40 kilograms less than or equal to m less than 50, and our second class is going to be 50 less than or equal to m less than 70. So we can see immediately that our class widths are not equal. The class width here is 10 kilograms, and in this one it's 20 kilograms. And then we've got the number of children, which is our frequency, F. So we've got 40 here, and we've got 60 here. So we want to illustrate this data on a histogram. So let's take note of our class widths. So the class width of this one is 10, and it's 20 here. And we've got frequency density is going to be, our frequency density will be 40 divided by 10, which is equal to 4, and it's going to be 60 divided by 20, and that equals 30, sorry, 3. So for the unequal widths, the masses are represented in the histogram by frequency density. So our y-axis is going to be frequency density, and it measures the number of children. So remember, this is number of children per kilogram. So let's now represent this in a histogram. So let's just read it in as 3 there. So we're going to have, again, on our x-axis we'll have that concertina bit here. And we'll start off at 40, and that's then going to be, I'll put 50 here, 60, 70, it's not very, maybe that wider actually. So we'll do 40, 45, 50, 55 we'll do. 50 here, 60, 70. There we go. So this is mass in kilograms. And up here we're going to have frequency density. So that's 3 and that's 4. So we'll do 1, 2, 3, 4. So that's frequency density. So between 40 and 50, we have a frequency density of 4. And between 50 and 70, we have a frequency density of 3. Now, what we want to work out is we want to estimate the number of children with masses between 45 and 63 kilograms. Now, when it says estimate here, what we're doing is we're assuming that there is an equal spread of children with masses over this, the frequency density is evenly spread over the column areas. And that's where the estimation comes in. So what we need to do here is, if we think about 45 is here, so that's 45, and 63 will be round about here. So we've got the it's straddling two classes. So what we need to do is split this problem up. So we need to work out the number of children between 45 and 50, and then between 50 and 63. So from this class we've got, for the class, let me just put this there, line there, the class 40 to 50 kilograms has a mid value range of 45 kilograms, and it has a frequency of 40. And so therefore, and for between this class, we're going to have half of 40 equals 20 children. Now for the next part, for the next range, frequency is width times frequency density. So the width here is between 63 to 50, and the frequency density is 3. So it's going to give us 13 times 3, which is 39 children. So the our estimate will be 20, add 20 from here, add 39 from there, which is going to be 59 children. Let's look at another problem. We're going to consider now times taken to the nearest minute. So we've got rounding happening for 36 athletes to complete a race. And it's going to be given in the table below. So time taken, and the number of athletes, time taken is 13 minutes. Just indicate the units. And there's 4 athletes, took 13 minutes. Between 4 and 5 and 15 we have 14 athletes, and between 16 and 18 we have 18 minutes. So this is a frequency. So let's consider, so now we're going to have gaps. So we're going to redo our table. So the time taken, t minutes. The number of athletes, and we're going to write in our class width and our frequency density. So if you think about the time taken for 13 minutes, so that could be 12.5 as the lower boundary, could be equal to the time, or it can be less, the time could be less than 13.5. So the next class will be 13.5, could be less than or equal to the time, and that could be less than 15.5. And finally we've got 15.5 less than or equal to t less than 18.5. This is the worst table in the history of tables. There we go. So we've still got the same number of athletes, 4, 14 and 18. Now the class width is 13.5, take away 12.5, which is 1. Here we've got 15.5, take away 13.5, which is 2. And here we have 18.5, take away 15.5, which is 3. So the class widths are different for each one. And now our frequency density is going to be 4 divided by 1 is 4. 14 divided by 2 is 7. And 18 divided by 3 is going to be 6. Now we're going to put this into a histogram, and I'm going to lose some of our data here, sorry. So if we, again, we're going to do the concertina thing, and our x-axis is the time, so we've got our 12.5, 13.5, that'll be 14.5, 15.5, 16.5, 17.5, and then over here is 18.5. And on this axis we've got our frequency. So we'll have 2, 4, 6, 8. So this is frequency density. So we've got 12.5, this was 4, Then 12 to 15 we had 7. I've lost in the last bit, but it was the frequency density was 6. That's meant to be on the 6. That's meant to be there. And this is our time taken, t in minutes. So make sure when you label your axes that you put units in as well. Now, we can use this to work some things out. So we want to use our histogram to work out the number of athletes who took less than 13.0 minutes. So we can see that in here, there's 13.0. There are 4 blocks. So if you look here, if we put 13.0, there's 1, 2, 3, 4 blocks to the left of the 13. So we have 4, which is the height, divided by 2, which equals 2 athletes. So if we think about each block represents 1 athlete. So if you just simply count the number of blocks and divide them by 2, we can estimate the number of athletes involved. So next question is the number of athletes who took between 14.5 and 17.8. So 14.5 is going to be here, and 17 is in the next class. So there are 14 plus 24 equals 38 blocks between here and 17, 16 here. There's 38 blocks, so 38 divided by 2 is going to be 19. And finally we want to know let's put this up here, the time taken to run the race by the slowest 3 athletes. So the slowest 3 athletes are represented by the 6 blocks. So 3 times 2 equals 6. To the right of the 18 block. So 1, 2, 3, 4, 5, 6. So here. 1, 2, 3, 4, 5, 6. So between 18.0 and 18.5 minutes is the time taken for the slowest 3 athletes. So I hope that helps.